Problem 5 on your recent homework asks that you sketch weight and displacement vectors for an object that rolls down one incline and up another. Don't need those glasses to see the board. Starting with the displacement vectors, we have a displacement vector that could indicate the travel down one incline, and another displacement vector that doesn't have to be contiguous with this one. We just draw it up the other incline. The vectors don't necessarily have to be the same length, and they can move anywhere on the page, but this picture will work just fine. And we have the weight vector. Okay, the weight vector being with having different units, it's going to be to a different scale. So we can really draw these vectors any way we want to, although we want the displacement vectors to have the right relative length to one another, and we want the weight vectors to have the same length. Okay, so that's it. That's the weight and displacement vector. Here's weight. Here's displacement. Here's weight. Here's displacement. Now, actually the problem was a little bit misstated. I didn't ask you to include the friction vector, but the friction vector, in this case, we have pretty much negligible friction, so no friction in this case. In the other two cases, you've got a little more friction and then even a little more. Now, for the intermediate friction, we could draw a friction vector, let's say this way and this way, opposite to the displacement vector. So here's a friction vector, and here's a friction vector. And we'd probably want to put subscripts, delta x1, delta x2, friction 1, friction 2 here, friction 1 here. The weight's going to be the same in both cases. In these two cases, the frictional force is less than the parallel component of the weight vector. So that if I project the weight vector onto the displacement vector here, or here, we see that the parallel component of the weight vector is going to be bigger than the friction vector, and that's the one requirement for the second question. So, I'll say the second situation, the magnitude of the friction vector is less than the magnitude of the weight parallel vector. And of course, the weight parallel vector is in the opposite direction. But since we're just talking about magnitudes, this will allow the ball to roll with an increasing velocity down the first ramp. Then, of course, when it gets onto the second ramp, it's going to have a decreasing velocity, both because the parallel component of the weight vector is back this way and the frictional vector is back this way. Okay? In the third situation, force of friction, I believe, is close to the magnitude of the parallel component of the weight vector. So, since the parallel component of the weight vector here, here's your weight parallel. That's not written in such a way that you can really see it, but you know what I wrote there. The friction vector could be considerably larger. Okay, and it would have to be almost equally large here. Now, the normal force in this case might be a little less or a little greater than the normal force in this case. The way I've got it drawn, this incline might be a little less than this incline. At least the way I drew the projection vector, it would appear that this incline has less slope than this incline. Of course, I didn't do the projections real accurately, so you can't really go by the picture. Now it's very possible over here that your friction vector would be greater than the parallel component of your weight vector. I'm not going to try to draw that in and label it like I did here. It's unnecessary. You've drawn this picture many times. You know where the parallel component of the weight vector is here. And I think I see people doing that pretty accurately. So the picture is going to look like this. Could well be that the friction vector in the second ramp then is greater than the weight vector, but it's not necessarily so. Depends on how you make the slope of the second ramp. Now, I'll confess that in stating the problem, I think I might have said this already, that I didn't ask you to draw the friction vector, but then to say what's different, I asked you only draw the weight and displacement vectors. So the bottom line is you should have the weight and displacement vectors. To explain what's different from one situation to the next, you would pretty much want to draw the friction vectors. No friction vector in the first case, a small friction vector in the second case, and a friction vector almost as big as the parallel component of the weight vector on the first incline in the third case. Naturally, on the second incline, in this case, the object is going to slow much more quickly. Friction is going to do work of much greater magnitude against the object, which means that you're going to have a greater negative work done by the non-conservative frictional force, which will imply a lesser increase in the potential energy, as we discussed in relation to the third problem. Many people went ahead and drew the normal force vector and other vectors, but a lot of times, as a matter of fact, I think in the majority of cases, what was missing was the displacement vector. Okay, you need that to have a picture of how the weight and the displacement go together to give you the dot product of the displacement and the weight. So we need to see this component of the weight vector, at least this projection, even if we don't draw the component in. And I guess that's the one thing that was kind of missing, and then there was a lot of other stuff that wasn't requested. Now, there's no harm in having that other stuff, but these are the only things that really affect the motion of the object, assuming a small incline, in which case the normal force will be pretty close to the size of the weight force.